Hello, we're on. I'm queuing up the PowerPoint. How was homework? No? I see some. It was hard? Good. Did you learn, though? I don't care if it's hard. I care if you learned. Okay, last time what we did is we talked about transformations on a random variable, and we did some simple transformations, and today what we're going to do is talk a little bit about the synthesis problem. We talked a little bit last time about the synthesis problem. The analysis problem is given a density function, given a nonlinearity, find the corresponding probability density function. The synthesis problem is opposite that. Given the density function you start with and the density function you end with, find the nonlinearity. So I mentioned last time the nonlinearity which maps to a if you're given the input and the output density functions, the nonlinearity which performs the mapping is not unique. In fact, it can take on a number of different forms, and I hope to convince you of that today. So let's start out with that for a synthesis problem. A synthesis problem. We're going to do a very easy synthesis problem, and that synthesis problem is to take a uniform probability density function on the interval from 0 to 1 and to generate a second probability density function on the interval from 0 to 1. So it's an identity mapping, right? You never want to do this. However, pedagogically, it's a very nice illustration of the fact that there's numerous ways that you can perform this mapping. For example, suppose that I had my function here, y, and this is x, this is my y is equal to g of x, and I wish to perform a operation, let's see, and I wanted a uniform density function from 0 to 1, so this is my density function, and I wanted over here sideways, this is my density function for my transform random variable, also from 0 to 1, with this corresponding density function. Now clearly a transformation which will achieve this is a unity transformation, correct? In the sense that every little piece of probability mass is mapped on this 45-degree line to its corresponding location there, right? So that's a straightforward analogy. However, I maintain that I could also do this same exact result. I'll try to do with different fonts and colors here. But I could also do it with this nonlinearity, y is equal to g of x. Because what does that do? That takes the piece here at 1 and maps it to the piece at 0, doesn't it? And it takes the piece at 0 and it maps it to 1. And I think you can see that exactly the same transformation holds even though I have a different value of g of x on both places. Do you agree with that? Just from the geometrical interpretation of the transformation of random variables? Here's another one. I maintain that this red triangle will also perform that transformation. Now, why is that? It's because if we look at a value here, a specific value of y, it gets mapped a little bit from here and a little bit from here. But both of these have a slope. Well, this has a slope of 2, this one of minus 2. Or let's see, yeah, 2, right, so we're around, yeah, 2, and minus 2. So this gets mapped over here, but it's only half as high. So this portion gets mapped over here half as much, right? It has half of the height. And this version over here also gets mapped over, and it gets mapped to twice the height. But you can see the overall effect is the mapping that we have achieved here. So the mapping is exactly the same for any of these three curves. Do you agree with that so far? Are you following my logic? Okay. We can also do other things. In fact, let me show you a few other things. If you're taking notes, you might want to draw this thing over again. Here's a unit box. I maintain that this will map also to a unity mapping. It's the same type of mapping before. A little bit of probability mass here gets mapped here, and a little bit here gets mapped here, and the overall result is this density function. Similar fashion, I think you can see that if we actually have any sort of sawtooth here, something like this will also afford a unity mapping. So my point is, in doing this, as I'm saying, in the synthesis problem, if you would like to synthesize a probability density function from another probability density function, chances are there's a very large infinity number of different mappings that you can actually perform in order to obtain the correct result. Because any of them that I put up there would actually afford the mapping from a unit to a unit. Now, that being said, we can restrict ourselves. One way we can restrict ourselves is look at the transformation, which is strictly increasing. If we restrict ourselves to, well, not strictly increasing, but say monotonically increasing, if we restrict ourselves to increasing functions, then the result there might be unique. In fact, for this case, the only strictly increasing transformation that gives you a mapping of the uniform in a uniform is the 45-degree line. That's the only strictly increasing result. So the other results deviate from being strictly increasing. But if you don't put that restriction on there, there's all sorts of different representations that you can have in order to characterize that relationship. Okay, let's return then to the overhead. Typically, in processing software such as MATLAB, we have available to us either uniform or Gaussian random variables. The transformation allows generation of other random variables, so this is where synthesis comes in. You're given a uniform or a Gaussian and you want an exponential, a Laplace, a gamma, some other density function. What do you do to that random variable in order to generate it? Well, when x is uniform, it's not difficult to show that y is equal to log of x gives an exponential random variable, that is a single-sided exponential, e to the minus x, and y is equal to tangent of x gives a Cauchy random variable. And again, as we mentioned here, the mappings are not unique. So here's the general synthesis problem for uniform random variables. Given a uniform random variable generated in MATLAB or C++, how do we generate a corresponding random variable such as an exponential? So given a uniform random variable on 0, 1, find the nonlinearity or a nonlinearity so that y is distributed only, or is distributed as fy of y, where this is a given function. So this might be an exponential, a gamma, a Cauchy, whatever. So we want to take a uniform random variable and we would like to transform it into a specified probability density function with a specified random variable. One of the solutions is y is equal to fx inverse of g. Let's pause and reflect on this a little bit. This actually is incorrect. This should be y. No, that's correct. That's fx inverse of x. Okay. The problem is this, is we're given y is equal to g of x as a transformation of a random variable. X is distributed as a random variable which is uniform on the interval from 0 to 1. So this is the corresponding density function. Now the question is, what is g of x, which will give us, once we perform this transformation, a specified f sub y. And don't forget, this is given. This is given. And the question is g is equal to what? Okay, for the synthesis problem. An answer, not the unique answer, but an answer is g of x is equal to f sub x inverse of x. You look at that and you go, well, wait a minute, isn't that the distribution function for the random variable? Yeah, it is. Oh, and it is incorrect. That has to be a y, doesn't it? F sub y. That's incorrect on the handouts also. So I was correct initially. Yes, it is, but you'll notice that this is, number one, a given function, because f sub y is given. So if f sub y is given, we can compute the distribution function for f sub y. Then we ask ourselves, well, what is the inverse? Well, remember that the cumulative distribution function is strictly increasing, right? Always, by definition. Therefore, the inverse is also strictly increasing by the arguments that we talked about last time. It just turns out now that we're bringing in the actual probabilistic description into the nonlinearity. Before, these were divorced from each other, but there's no reason that they can't be coupled. There's no reason that they can't be coupled. And so this is a solution. And it actually makes a lot of sense. Let's look at the density function for y. That's equal to the probability that y is less than or equal to y. This is the density function for y. Well, what is y? Y is equal to g of x in general. And we're going to say that this is the probability that f sub y inverse of x is less than or equal to y, because this is the nonlinearity that we're choosing in order to affect this transformation. Now we are going to operate on both sides by f sub y. Remember, f sub y is strictly increasing, so therefore we can operate on both sides of the inequality with that function without disturbing the inequality. So we're going to operate on both sides by that. Whoops, forgot on the right side here. And of course, on the left side, what do we have? This is a function operating on its inverse, so we get back the original function again. It's like log of e to the x, right? So we get back the original function. Whoops, this should not be an inverse here. This should just be the f sub y of y. Okay, so let's remember this as we go to the next board. Any questions on this so far? We have yet to reach our final solution. For a uniform distribution, that is on the interval from 0 to 1, f sub x of x is equal to something with a linear slope of x on the interval from 0 to 1. That is, if we were to take the uniform random variable and we were to integrate it to get the cumulative distribution function, this is the result that we would get, right? So let's remember that. For the uniform, f sub x of x is equal to x as long as x is between 0 and 1. With that in mind, let's recopy the solution we had at the bottom of the previous board, that f sub y of y is equal to the probability that x is less than or equal to f sub y of y. But you'll notice that this is nothing more than the cumulative distribution function. Remember, I said anytime you had the probability a random variable is less than or equal to whatever, a smiley face, that was the distribution as a function of the smiley face. Remember that? So here we have nothing more than the distribution function of x, except that the argument is f sub y of y. You with me? But what is f sub x? F sub x is an identity operator, right? F sub x is an identity operator as long as what it's operating on is between 0 and 1. Well, this is always between 0 and 1, isn't it? This is always between 0 and 1. Since this is always between 0 and 1, we end up generating, if you will, an identity, and this is one of these kind of proofs where you start out with assumptions and you show 2 is equal to 2 at the end is a logical conclusion. And so we have the distribution that we generate is indeed the distribution function for y, which is what we wanted initially. So we have shown that, in fact, we are generating this distribution. Okay? So this is the synthesis problem. And let's go back to the overhead, and let me show you what the summary is. Given a uniform random variable on 0 and 1, we want to find the nonlinearity y is equal to g of x so that y is distributed as some given density function. One solution, not the solution, but one solution is that y is equal to f. This should be a y subscript, not an x. Should be a y subscript, not an x, as a function of x. Okay? Interesting problem. Which lets me know, for example, suppose that I wanted y distributed as e to the minus y times u of y. And I wanted to generate a random variable which had this density function, but all that I had available to me in MATLAB was an x. So x is uniform. So x is uniform. What transformation do I do on this uniform random variable in order to give it this density function? Well, one of the solutions is give my g of x as equal to f sub y inverse of x. Well, what is that equal to? Well, if the density function that we want is equal to e to the minus y times u of y, I think I'm being inconsistent. This is mu corresponding to a unit step. If f sub y is equal to e to the minus y, then this means that the cumulative distribution function as a function of y is equal to 1 minus e to the minus y times mu of y. In other words, the integral of this gives this. Okay? Okay, well, what is f sub y inverse of x? Well, that means we have to go here and we have to solve for y. So let's assume that y is positive. Let's assume that y is positive. I'm going to rewrite the equation on the bottom of the board. And now we'll solve for y. And again, I don't want to explicitly put there. We'll just assume that y is positive. Remember, y is positive. Y is positive. So we call this equal to x, and we need to solve for y. So e to the minus y is equal to 1 minus x. So that means y is equal to minus log of 1 minus x if we solve for y here. This then is the inverse of that probability density function, or distribution function. And this will transform the uniform random variable into a exponential random variable. Let's draw a sketch of it. Here's our typical sketch. F sub x of x is uniform on the interval from 0 to 1. And over here, we want an f sub y of y to be an e to the minus x. We are saying that our nonlinearity, g of x, is equal to minus log of 1 minus x. Okay, for x is equal to 1, what is this equal to? Looks like it's infinity, right? For x is equal to 1? Yeah.
That'd be f sub y of y.
F sub y of y. Yeah, thank you. Yes, it should be a f sub y of y. For x is equal to 1, this is equal to infinity, and so it's kind of a backwards logarithm. It kind of comes down like this. So this is the equation for minus the log of 1 minus x. And you'll notice if we look at it sideways, if we solve for x here, what do we get? X is equal to 1 minus e to the minus y from up here, from this equation up here, right? So if we solve for this. So therefore, I think you can see some of the things which are happening. For very high values, if we have a high value, the probability mass is going to be mapped to a very large interval, right? So for a high probability mass, we get that mass spread out over a long interval since we have a very high slope there. Make sense? Whereas for very small values, well, we actually get compression, and indeed what we get here is this result which we want, e to the minus y. Remember, y is greater than 0? We required that. Well, y is greater than 0. We just chop it off and make sure that it's equal to 0 for negative time. Doesn't matter anyway. We don't have any mapping for y less than 0. So it becomes something which is moot to even consider. So this is an illustration of synthesis of a random variable, of synthesizing this exponential random variable from a uniform random variable using the cumulative distribution function of the random variable we wish to generate, in this case, an exponential. We could have applied this to any density function that we so desire. Any density function that we so desire. Any questions on this? There's a converse problem, and I can even illustrate it here. The converse problem is this. Given an arbitrary density function, we want to find a nonlinearity which maps it into a uniform random variable. Let me say it again. Given a random variable with an arbitrary density function, we would like to map it into a uniform random variable. This is the converse of this problem, which is mapping the uniform random variable into an arbitrary random variable. Now we want to do the converse. Well, you notice this mapping is kind of two ways, right? If this maps into this, then this should map into this. It's kind of a converse mapping, okay? Or a bilateral mapping. I don't know what you call it. But anyway, you can go both ways here. You can go both ways in terms of the mapping. So the synthesis problem is actually taking this and bouncing it off the curve here, which is going to be a function of the density function that you start with in order to get a uniform. And we'll go over the details of that just in a second. But the use of this, again, is in non-parametric statistics. We are given a random variable and we have no idea of the underlying density function. The only evidence that we have of the underlying density function is a histogram. We've taken a histogram of a lot of different points. And as you've seen, if we make the bin sizes small enough and we take enough samples, we can use this histogram as an estimate of the probability density function of the underlying random variable. Therefore, we can take that histogram, and once we have that histogram, we can estimate the corresponding density function. So with a histogram, we can estimate the underlying density function by normalizing the histogram to have unit area. Then we can also estimate the cumulative distribution function. I'm not sure in C. In MATLAB, there's a very nice operation called cumulative sum, or CUM, SUM, which actually computes the equivalent of an integral because it does a cumulative sum of all of the elements in the vector. And indeed, if you have f sub x stored in a vector and you put cum sum on that vector, you actually have generated the density or the cumulative distribution function immediately in the MATLAB operation. So in other words, we can get this as a vector, then we can get this as a vector, and then in order to get a uniform random variable, so we want y is equal to uniform on the interval from 0 to 1, The synthesis problem is to find a g of x to perform this operation from a general cumulative distribution function to a uniform. And the one that we can always use is f sub x of x as the transformation. So therefore we have our arbitrary density function here. We have our corresponding nonlinearity. By the way, somebody took me to task for calling this a nonlinearity. It can be linear. It's just in general that it isn't. But we're going to choose this as a nonlinearity of y is equal to g of x, which is equal to f sub x of x, which is actually the cumulative sum of this thing integrated. So I don't know what it would look like, maybe something like this. And we're assured that this cumulative sum, which is the distribution function, ends up at what point? 1, because the cumulative distribution is always between 0 and 1. So therefore, immediately we see, without seeing the exact structure, that no matter what, the mapping is going to be that it is going to be from the interval from 0 to 1, since that's the only interval that that distribution function follows. And indeed, that's the case. We do get the uniform distribution function here as the f sub y of y. That's the result. So this is the other synthesis problem. So again, if we go back to the overhead, the converse problem is given f sub x, find y is equal to g of x, so that y is uniform on 0, 1. We have just illustrated that one solution is y is equal to f sub x. You should be able to prove that, much like we proved the last result. Again, I want to emphasize these solutions are not unique, or not the easiest computationally. If, for example, you have a uniform random variable and you want to make a Gaussian random variable out of it, then you have to use a nonlinearity of an inverse error function, which is very difficult to numerically to compute. There are easier transformations which will allow you to do this, however. But this is a brute force one. Okay, one of the most common functions of a random variable are expected values. And these I'm sure you're familiar with to one degree or another. The expected value of g of x, that is, we have y is equal to g of x. We affect a transformation just like we did before, and we want to find the expected value of this transformation. That's equal to, by definition, the integral over the function we're trying the expected value of times the corresponding density function. There's a number of these which you've seen before. There's the nth moment, the expected value of x to the n. The kernel here is x to the n times the density function, the integral over that. The most commonly used moment is the mean, or the center of mass of the density function. That's the expected value of x, which is equal to the integral of x times f sub x of x. This is actually the center of mass of the item. It is not the division of the density function 50% on one side, 50% on the other side. It is not that as the center of mass. If you cut the density function out of a piece of wood, it would be the point where you could balance the density function. And that doesn't mean halves on one side and halves on the other. When you have half on one side and half on the other side, they call it what? The median. Yeah, the median. And the mean in general is not equal to the median. Sometimes it is when you have symmetry going for you. And then there's the variance. The mean, by the way, is a measure of central tendency. Your boss might come to you and say, I don't want to know all that stuff about the density function. I just want a number. What does it mean? Well, if you want to give one number on what the random variable represents, you usually give the mean, or the center of the mass. A second characterization of the density function is the variance. The variance, of course, is the second moment minus the square of the first moment, and is a measure of the dispersion, or how much the density function is spread out. If you have a density function which is really spread out, it'll have a high variance. Something which is very compact, you have a very, very small variance. So here's the definition of expectation. There's the assumption in writing these down many times that these moments exist. There are density functions for which these moments do not exist. Let me give you an example. If you take this random variable, f sub x of x equal to 1 minus 1 over x for x greater than 1. This is very nice because it goes from 0 and asymptotically it goes to 1. So therefore it's a perfectly good random variable. It's a perfectly good cumulative distribution function for a random variable. Yet, if you were to try to compute the mean of that, you would find something interesting. So this is the distribution function that we're talking about, the density function. You'll notice, first of all, this is continuous at x is equal to 1. There's no discontinuity. So when I differentiate, I won't have any direct deltas. Okay, it's continuous. So when I differentiate, I want to have a 1 over x squared times mu of x minus 1. Well, this is fine because this does have an area of 1. If you were to integrate this function from 1 to infinity, you would come out with 1, I think. Doesn't look great here. 1 to infinity. Yeah, it works out good. Right? Well, it has to be, because if you integrate it from 1 to infinity, you'd get this evaluated at x is equal to infinity, which is equal to 1. So yes, it does integrate out to 1. However, if you compute the expected value of this, if you computed the expected value of this, it would be the integral from 1 to infinity times x, this is the expected value of x, times the 1 over x squared dx. So it's equal to the integral from 1 to infinity of 1 over x dx. And you know that the 1 over x curve has an infinite area. This is equal to the log of x between 1 and infinity, which is equal to infinity. So here's a random variable whose expected value is, its mean is infinite. Or more rigorously for mathematicians, the mean doesn't exist here. So means don't always exist. In a similar fashion, variances don't always exist, in the sense that second moments don't always exist. Let me give you an example for the Cauchy random variable. Cauchy random variable, the density, is equal to 1, well, let's just say a constant over x squared plus beta squared, where the constant gives it so that we have a total integration of 1. If we were to look at the second moment of the Cauchy random variable, we would have the following. We would have an expression which looks like this, correct? Yeah, it should be x squared, thank you. Let's look only at the integrand here. If we look at the integrand, what does the integrand look like as a function of x? As a function of x, this integrand asymptotically approaches for large values of x what number? 1, right? What about for negative x as it goes to minus infinity? It also goes to 1, doesn't it? Right? So therefore, if we were to just look at the integrand of this, it would look something like this. I submit. That's what the integrand would look like. This has an infinite area, doesn't it? So here the second moment is equal to infinity. The first example I gave you, by the way, the second moment is infinite also. But here we have a second moment of a commonly used random variable where indeed the second moment is infinite. So therefore, in many cases, we will talk about if you take a random variable with a given variance or a given mean. Anytime we say given a random variable with a given variance and a given mean, there's the assumption that that mean and variance do exist. There's the assumption that the mean and the variance do exist. They don't always exist. And here are two examples of where they don't exist. We also have lattice random variables. These are the discrete random variables. In such cases, the expected value definition simplifies, and the expected value of g of x is equal to the summation of the probability mass function times the nonlinearity that we're talking about, g of n. Example lattice discrete random variables, again, are the Poisson, the binomial, and the Bernoulli random variable. For lattice random variables, the nth moment, the expected value of x to the n is equal to the probability mass. This, by the way, should not be a minus sign. It should be an equal sign, times k to the n. I'll try to remember to correct that and put it on the web. What's interesting about the mean is that it not be realized in the actual random variable. I don't know if you've ever seen the little trick you can do in restaurants with 2 forks and a toothpick, where you take 2 forks and you stick them together in an angle like this, and then you put a little toothpick out, and you can balance the 2 forks on the toothpick that sticks out in the V between the forks. Has anybody seen that? It's a little restaurant trick. Okay. Well, this shows, well, it's an optical illusion. You look at it and you go, wow, how can that happen, that center of mass be out there at the end of that toothpick, which isn't even near the forks? Well, this is an example of the center of mass, or the mean of the random variable, in this case the distribution of the mass of the forks, not being a part of the mass of the forks. And this is something which can happen in random variables. Very simple example. Suppose you flip a random variable. You flip a coin, and you assign the random variable of 0 to a heads and a 1 to a tails. Well, the expected value of your output is equal to 1/2. Yet you cannot have 1/2 as an output, right? So this causes people to have problems sometimes. I think it's fine. But it does point out that just like the fork balancing problem, that here we have a random variable whose expected value is not even an outcome. So how can you have an expected value which is not an outcome? Very interesting. So the point is that the expected value need not be a realizable value of the random variable. Here's an interesting problem which affected Bernoulli, and I'm going to give it to you. It's another one of those interesting problems. And it's a problem having to do with gambling. Here's the problem. You run a casino, and here's the game we're going to go play. I'm going to come in and I'm going to flip a coin. I'm going to flip a coin, and if I get a heads, you give me $1. If I flip a tails and a heads, you give me $2. If I flip a tails, tails, and heads, you give me $4. Tails, 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 heads, $8. In other words, I flip the coin until I get a heads, and then you pay me 2 to the n flips. Do you understand the problem? The gambling game? Now the question is, if you own the casino, and I came in and I wanted to play that game with you, what should you charge me to play that game? Typically in casinos, they take the expected value and they add a little bit to it, right, so that they can make a profit on their games. So the question is, what should you charge me in order to play that game? Well, you should charge me whatever the expected value of your winnings is, plus a little bit. If you charge me that, then you would always make money in the long run by what we'll call the law of large numbers, which we'll talk about later. Do you agree with that? So let's take a look at this specific game. Okay, let x be the number of coin flips before the first head. Clearly, the probability that x is equal to k is equal to 2 to the minus k, where k is the number of flips. So the probability it takes me 3 flips is a tails, tails, heads, which has a probability of 2 to the minus 3, or 1/8, right? The payoff is 2 to the k dollars. In other words, I take how many times you flipped. I'm going to take $2 and raise it to the kth power, and I'm going to pay you that amount of money. So what we want to do is compute the expected value in order for you to figure out what to charge me at your casino when I play this game. If you ran this game in Las Vegas, what would you charge to play? What is the expected value of x? Here's the interesting result. The expected value of the money that you make is equal to the summation, of k is equal to 1 to infinity, of the money you would make on the kth flip times the probability of the kth flip. This is the definition. This is the definition of expected value, right, for lattice random variables. But this is equal to 2 to the k. This is equal to 2 to the minus k. Right? And the result is equal to infinity, which is a wild, unexpected result, one that does not initially set well with your intuition. Well, what does this mean? This means that if you ran this game and I came into play, there's no amount of money that you could charge me that would be enough. Now don't forget, this is for one flip, $1, two flips, $2, three flips, $4, four flips, 8, five flips, 16. And you wouldn't even accept from me $1 billion to play that game? I mean, this is what this result is saying, right? You understand? It's a very strange and peculiar result, which I believe historically was first noted by Bernoulli, and it was the topic of some philosophical discussion. Does anybody have any answer, any resolution to this inconsequence? By the way, if you paid me $1 billion to play that game, I'd let you play. Okay? I would let you play. So in one sense, it doesn't sound reasonable, right? Would you take $1 billion for me to play that game with you? Yeah, absolutely. But the math says infinity. You'd be a fool to take $1 billion, even $1 trillion, because the expected value of my winnings is infinite.
So what's MATLAB say?
Huh?
I mean, presumably somebody's done some sort of simulation on this.
Yeah, try to simulate it. And you'll find out if you let this run, this number gets bigger, bigger, bigger.
It just
bigger,
keeps.
Yeah. If you let it run forever.
Too bad that we're unlucky.
No, I guess so. I guess so. We're betting that you're unlucky.
What's the second moment?
Second moment's also infinite. So is the third and fourth and fifth. They're all infinite. Why don't you think about that and maybe tell your friends this and see if you can do a sucker bet for them and get them to pay you $50 to do the coin flipping. I'm not going to tell you the answer. I'm going to let you think about it. Then if you come up with the answer, an idea of what the answer is. By the way, I've done no math trickery here. There's no tricks that went into this, okay? I haven't concealed a deep mathematical truth like we did on Bertrand's paradox. This is the actual result for that game.
What do you mean come up with the answer? You said the answer's infinity.
Yeah, the answer's infinity.
So.
Okay, by the answer I mean the following. It doesn't square with intuition. And I maintain for any math to make any sense, it has to make sense, right? And in some way, yeah, this is the math, but it doesn't make sense. There's other things that don't make sense. For example, in math, I could do a statics problem on this, and I would say I drew all the force vectors, and if I drew all the force vectors on this, if I lift my finger, are going to be 0, right? Right? In theory. So therefore, if I lift my finger, that'll stay exactly where it's at. Because there's no external force acting. Well, it doesn't work, okay? I didn't have to do that to let you know it didn't work. So there's an example where the model, and probability is nothing but a model. Don't forget, probability doesn't exist. It's just a paradigm and a way of thinking about things. How do you square that model with reality and your engineering knowledge of the world? And the fact that there's just something in you that says that I offered you $1 billion to play this game, that even though the math said infinite, you'd probably take that $1 billion. And you'd probably lose $32.64, $128, 1,000 and whatever the power.
Amount of time to play, though, right?
Huh? No, it's just for one game. One game. My expected winnings in that one game is infinite. So think about that. So therefore, we think we have a good handle on expected values, but the Bernoulli's gambling paradox is, it's not a paradox, it's a gambling problem. It's just a very interesting manifestation of
You think
things.
Bernoulli had a gambling problem?
Yes, he did. Well, in fact, it was very interesting. During the time of Bernoulli and Pascal, I mentioned with Pascal, his dad tried to keep him away from math because he wanted him to study Latin. Their big thing at the time amongst ladies and gentlemen was gambling. And so therefore a lot of the early probability was actually developed in the area of gambling. In fact, Pascal actually put his propositions forward in theology using probability. There's a famous, if you look at Pascal's wager, which is a philosophical argument about whether God exists or not, it's totally couched in a probabilistic framework. So this was the way that people thought at the time, and was the language of communication at the time. So yes, he probably did have a gambling problem. At least he was knowledgeable of it, and these were the people that first began to model it. One of the most important expected values, besides the mean and the variance, is the characteristic function. The characteristic function is something which we will talk about after our break. I know this is 25 minutes afterwards, so this will be a good time to break. So let's go ahead and take our break and meet when the big hand's on the 6th. We'll come back and initiate our talk about characteristic functions. Thanks for your time. Hi. I was in the homework. The homework again is due on Thursday. And you're right, I was remiss. I didn't allow for the scheduling of the off day that we had last Thursday. So we will rephase, and I'll begin assigning homework again on Thursday. So Thursday will be your next assignment. Okay. Let's return now to those thrilling topics of probability and talk about characteristic functions. Characteristic functions, the mathematicians offer them as the expected value of e to the j omega x, and if you substitute this into the definition of the expected value, you get this expression. In other words, whatever we're expectating here appears as the kernel over here. You'll notice that what we're left with is kind of the Fourier transform. The only difference is it's a Fourier transform of the probability density function, except that instead of a minus j, we have a j. You're probably used to e to the minus j omega t in terms of Fourier transforms. We simply have a j omega x here. And the only difference here, you can use all your old Fourier transform tables for e to the minus j omega t, except everywhere you see a minus omega, now you stick a plus omega, and you're okay in your transforms. So the Fourier transform, and we will refer to this as a Fourier transform, of the probability density function is referred to as the characteristic function of the underlying random variable. The characteristic functions have important properties. One is that the value at the origin is a absolute maximum. That is, everywhere else at the origin, this is equal to 1. And also this should be the expected value of x raised to the nth power. The expected value of x raised to the nth power is the result that we have here. Huh. So let me indeed illustrate that. This is the definition of the characteristic function. If we evaluate the characteristic function at the origin, we obtain this expression with this e to the j omega x set to 1. Since omega is equal to 0, that e to the j omega x goes to 1, and we're left with the area of the density function. And the area of the density function, of course, is equal to 1. Right? So the characteristic function at the origin is equal to 1. The second equality comes from this expression. The following inequality is kind of intuitive. that the magnitude of the integral always has to be less than or equal to the integral of the magnitude. Let me explain to you why this is intuitive. The only time that this can be zero, this can be zero for a lot of different f's and e to the j's. In fact, the integrand just has to be something that wiggles above the axis as much as below the axis, right? So there's a number of integrands here which this will integrate to zero. Whereas over here, this will never integrate to zero unless f is identically zero. Okay? So this inequality follows. And of course, this is the same thing as the product of the magnitude. The magnitude of the product is the product of the magnitude. What's the magnitude of e to the j omega x? This is equal to 1. And we're left with the integral of the magnitude. Well, heck, f sub x is positive anyway, right? Or non-negative. So we don't have to worry about that absolute value sign. And we know that this integrates equal to 1. So this is the second part, is that the value of the magnitude of the characteristic function is always less than or equal to 1. And that value of 1 is also equal to the value of the characteristic function at the origin. So these are two characteristics we would always expect from characteristic functions. There are, if x and y are independent random variables, then the characteristic functions, just like the density functions, multiply each other. That is, the characteristic functions, if the random variables are independent of each other, then phi of x plus y is equal to the product of the individual characteristic functions. Now, what's interesting about that is that if they're independent, if they are independent, then it turns out if we perform a inverse Fourier transform on this, what happens if we multiply two functions in the frequency domain? What do we do in the corresponding time domain, or the x domain in this case? We perform a convolution, correct? We generate a convolution. So indeed, this comes out to be a very interesting result, that if we add two independent random variables, that we perform a convolution of their underlying probability density functions. Let me, in fact, give you an example of that. We will actually delve more into detail about this when we get into the chapter on multiple random variables. But this is a good place to talk about it when we start about random variables. Suppose that x is the dots on a die, and that y is equal to the dots on a die. So we're going to throw two die. Now, the outcome of the two dice is going to be independent from each other. The outcome of one is going to be independent from the outcome of the other one, correct? If we were to look at an individual density function for f sub x and f sub y, they would both look like this. So they would all have a outcome which looked like this. That is a uniform random variable, correct? For each individual die, a uniform discrete random variable, wherein the outcome of each one was equally probable. Do you agree with that? Now, let's talk about rolling two dice. We're all expert at monopolies or crap, or I'm sorry, craps. And we all know what the outcome is. Now, you know, if you roll two die, what can you get? You can get anywhere from 2 to 12, right? So let's mark off our axes here in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now, what is the chance when you roll two die that you get snake eyes, or a result of 2? It's one chance in 36, right? So we're going to put here, we're going to make little ticks off here in 36ths. 1, 2, 3, 4, 5, 6. So right here is a sixth. So we have a little delta function here with a probability of mass equal to 1/36. What's the probability of getting a 3? What's the probability of getting a 1 and a 2 or a 2 and a 1? Right? Which is 2/36. Probability of getting a 3 or a 4? 3/5 because you can get a 3 and a 1 and a 3, or 2 and a 2. Similarly for 5, it pops up because you get a 4 and a 1 and a 1 and a 4 and a 3 and a 2 and a 2 and a 3. And then it maximizes, no, it doesn't maximize out here. It comes up here to 5/6 for 6, and then 7/6 for 7. And then, as you know, it starts going back down, doesn't it? 8, 9, 10, 11, till finally we get boxcars, which are 2 6s. That has a probability of 1/36 also. So these are two probability density functions that we're familiar with. So this is the density function for x plus y as a function of x. Notice, this is the convolution of this with itself, right? And this goes to the underlying theorem that I just put up there. If you add 2 independent random variables to get a third random variable, that third random variable, if the initial 2 are independent of each other, will have a density equal to the convolution of the first 2. Very interesting result. This is also, as we mentioned here, the foundation of the central limit theorem. We will be going over this more in detail later in the course. But the idea of the central limit theorem comes from convolutional properties, which says if you take any functions, almost any functions, and you convolve them 1,000 times, you'll come up with something which is pretty close to a Gaussian. And you'll notice that this is not a Gaussian, but is certainly closer to a Gaussian than this uniform. And if we did it again, if we rolled 3 dice, guess what? This would be, it would start bell-shaped just with 3 terms. And this is true of almost any underlying density function. When I say almost, what do you think is excluded? Our old nemesis, the Cauchy, right? Because one of the requirements is that in order for this property to hold, that the underlying distributions have to have finite means and variances, and the Cauchy doesn't have a variance. So again, this might be a little opaque to you at this point, but it's something I thought I'd tease you with, and we'll see a little bit later. There's also something, can we get the top here? This is not in your book, but I think I want to put it in here because it's very important and very nice in terms of doing calculations. This is called the second characteristic function. The nice thing about the characteristic function is the following relationship. Is that it's very nice for generating moments. This is the definition of the characteristic function. Notice what happens if I differentiate this k times. If I differentiate this characteristic function k times, well, what do I do? Can I take the derivative past this integral? Yes. When can I do that? Always, right? Okay. Can I take that derivative past here? Yeah, because it's not a function of omega, is it? So the only thing that really is differentiated on is this e to the j omega x. And what happens there? Well, this e to the j omega x brings down to e to the jx k times. Which is kind of interesting, right? Brings it down k times if we differentiate it k times. So therefore, if we look at the derivative and we evaluate the kth derivative at the origin, so the kth slope, if you will, that turns out to be j to the k times f times x to the k times f sub x of x dx, which is recognized as j to the k times the expected value of x to the kth power. Okay. By the way, I will use an equivalent notation interchangeably, where expected values will be denoted by overlines. That's just an alternate notation for expectation, is all. So this is interesting. If we take the characteristic function and we take the kth derivative of it, we obtain the kth moment of it if we evaluate that kth derivative at the origin, times a little fudge factor, which we have to take out here. So therefore, if we have the characteristic function, we first of all do a sanity check by making sure the characteristic function at the origin has to be equal to 1. And you notice that's kind of the 0th moment. That's the expected value of x to the 0th power, which is just the area of the density function. Then phi prime x at 0, that's one derivative, is equal to j times the first moment. And then phi sub x double prime at the origin is equal to minus the second moment, the minus sign coming from a j squared. And we could go on generating all of the moments this way. So that's one of the nice things about the moment generating function, is the ability to generate moments. One of the bad things about it, however, is that if you actually apply it to a density function, you compute the transform and then do these derivatives, once you get here, you get this second moment, then you got to go back, because you really don't want the second moment usually. You want the variance. You got to go back, you got to square this result, and then you got to subtract them and simplify and things like that. So it works very well on moments, but it is not as nice as the second characteristic function, which we'll look at right now. The second characteristic function is defined simply as the logarithm of the first characteristic function. Very simple definition. The nice thing about the second characteristic function is that if we take the derivative of the second characteristic function, just like the first characteristic function, we evaluate it at the origin, we get j times the first moment. However, the second characteristic function is nice. If we take the second derivative and evaluate it at 0, we get minus the variance. It's not the second moment, but we actually get the variance with everything topped off. By the way, the moments of a characteristic function are, of course, the moments. There's a field of statistics that talks about the second characteristic function and its moments. They're referred to as cumulatives as opposed to moments. So let's indeed show this. Phi sub x is equal to the log of the characteristic function. And so therefore the first derivative, we know of the log, is equal to phi sub x prime of omega divided by phi sub x of omega, right? Derivative of the log with the chain rule applied. Hello, right? Gosh, go back and look at your derivative of logs, please. And anyway, if we look then at the second characteristic function, evaluate, this should be omega, by the way. If we evaluate this at omega is equal to 0, we get phi sub x prime at 0, which we've already established as j times the expected value of x, right? In the numerator, right? And the denominator, what do we get? 1, so it's equal to jx bar. Kind of cool. Okay, now we do the second derivative. And we all remember our rules for definitions of quotients, right? Remember, it's the bottom squared times the denominator times the derivative of the numerator. Do you remember those? Minus the numerator times the derivative of the denominator. and they're both the same. Right? So therefore we obtain 1 times what is this evaluated at the origin? We said that was equal to minus the second moment, correct? Then we subtract off this j times x bar squared, because that's what the first derivative evaluated at the origin is. And then in the denominator, we have just simply 1. Well, you notice that the top is nothing more than minus the second moment minus the first moment squared, which is equal to minus the variance of x, which is very nice. So this is usually if you have a characteristic function, you want to compute the mean and the variance, this is the formula you go to, not the characteristic function. If you want to compute the mean and variance, almost always. There's a moment generating function also. We will not deal with the moment generating function in here, but the moment generating function is similar to the characteristic function in that it is the expected value of e to the minus sx. Well, if you compute that, you get the integral from minus infinity to infinity of the density function times e to the minus sx dx, and we in double E know that's a Laplace transform. So we can Laplace transform the PDF, or we can Fourier transform it. We know that there's many similarities. You'll notice there's one difference maybe between the Laplace transform here and the one that you're used to. The one here is bilateral. The integration is over all values of x. You might have been introduced to the unilateral Laplace transform, which is just from 0 to infinity. And indeed, in many cases, not all cases, this is a PhD qualifying exam question, by the way. When in the bilateral Laplace can you substitute s by j omega and get the Fourier transform? Can you always do that? Interesting question. You usually can, but not always. And why can't you always? So we have the Laplace transform. The Laplace transform we won't deal with the Laplace transform very much. But the Laplace transform is also known as the moment generating function if the minus s is an s. So there's all sorts of different perturbations in here. And then there's the moment generating function is the Laplace transform evaluated at minus s. But we won't be dealing with that. Just like the Fourier transform, you can use the Laplace transform to generate the moments, and we won't go into that very much either. Now, when we have discrete random variables of the lattice type, we have a sequence of probabilities, which are, the density function is a sequence of probabilities. When we have a sequence of numbers, usually we think of sequences of numbers as what? Kind of a discrete signal. And we treat discrete signals using z transforms. And indeed, if we have a discrete random variable of a lattice type, we can talk about the z transform of the probability mass function. And the z transform of the probability mass function is as follows. P sub x of k is the probability that the random variable x is equal to k. And we simply multiply that by z to the k, and we sum over all values of k. This then is referred to as the probability generating function. So therefore, we have seen that we can take density functions and we can Fourier transform, we can Laplace transform them, we can also z transform them if they're discrete. And as you know from your previous work in z transforms and Laplace and Fourier transforms, there's interrelations among these different transforms. From the probability generation function, we can also compute the mean and the variance. Here is the result. I will let you look this over at your leisure. But the expected value of x is equal to the first derivative, not evaluated at the origin, but evaluated at 1. Remember with z transforms, we talk about the unit circle. whereas with Laplace transforms, we talk about units of convergence along the parallel to j omega axis, or on the j omega axis. So this is the g is equal to 1 term. We can similarly get the variance. It's a little bit more complicated and concocted, but indeed is something that we can get directly from the probability generating function also. Next, I'm going to give you on the slides a number of common models that we've looked at previously. I will state their density functions, their characteristic functions, their Laplace transforms, and if they are discrete random variables, their probability generating function. This is just for reference. I'm not going to sit and read through them all, but I'm going to show you the ones that we have here that are available to you in the downloadable slides. So here we have the Bernoulli. This is the characteristic function for the Bernoulli with the Laplace and Laplace transform and the moment generating function, because the Bernoulli is indeed a discrete random variable of the lattice type. Here's binomial, geometric. Did you get the binomial? Okay, binomial. Geometric. The ability to generate these characteristic functions is a prerequisite for the course, so hopefully you've seen at least the characteristic functions before. Here's the Pascal or negative binomial, characteristic function, moment generating function, all of the different functions that you love. By the way, each of these characterizes the random variable. If I came to you and I says, I want to talk about a random variable, you could give me the characteristic function, give me the Laplace transform, or you could give me the density function, and that would all be the same information. Because in all cases, I can get all of the others given one. You give me the density function, I can give you the characteristic function, the Laplace transform, and the moment generating function. Okay? If you give me the Laplace transform, I can get the density function. I just do an inverse Laplace transform on it, right? So these are just different characterizations of the same phenomena, the same random variable, underlying random variable. And given one, you should be able to pop around to go to the different ones. Of course, again, the moment generating function is restricted for discrete random variables of the lattice type. Here's a uniform random variable. Gaussian random variable. Gaussian random variable is kind of interesting in that its Laplace transform doesn't converge. So therefore we're restricted to look at the Fourier transform. And of course it has no moment generating function. Why? Because it's not discrete. Here's exponential, Laplace, gamma. And that's it. That's all I gave you, gamma. We'll end up today's lectures, and in fact this will end up all of the prerequisites for the course by reviewing tail inequalities. We'll look at two. We'll look at the Markov inequality, then we will look at the Chebyshev inequality, both Russians. Okay, here's the Markov inequality. Markov inequality relates probabilities and for unilateral probability density functions. It's unilateral in the sense that the density function is equal to it only has mass for positive argument. In other words, the density function is 0 for negative x. Under that case, we have what I'll refer to as a unilateral density function. If we have such a unilateral density function, a uniform random variable on the interval from 0 to 1, an exponential random variable, a Rayleigh random variable, a gamma random variable, a binomial random variable are all examples of random variables which are unilateral. They're identically 0 for negative argument. If you have any of these, the probability, and it relates the probability to the mean, and in a way illustrates the mean as the central tendency, although we know from statics that the mean is the central tendency. It's the ultimate central tendency. It's the center of mass. The probability that the random variable x is greater than or equal to a is always less than or equal to the mean of the random variable divided by a. This is always true for unilateral random variables. It means the following. if we have a density function such as this exponential here, we have a density function such as this exponential, this density function has a mean. By the way, we're assuming a mean exists, right? Remember that 1 over x squared for x greater than 1? Mean didn't exist. It's still meaningful, because if the mean's infinity, we're saying the probability is less than infinity. Yeah, that's probably true, right? So it works, but it's kind of degenerate. Also, you notice that sometimes x bar over a can be like 7, right? You're saying the probability is less than or equal to 7. That's, so what? You don't learn anything from that. You already know the probability is less than 1. So sometimes this inequality is going to give you stupid, useless results. If x bar, say, is 7 times a, right?
The mu of x, is that just a step?
Mu of x is a unit step function, also called a Heaviside step function. And this is our definition of unilateral. Okay? So it says that if we have one of these density functions, we have an x bar and we have a value of a, the probability that x is greater than a, which is equal to the area under this tail, is always less than or equal to x bar over a. Interesting result, and one that isn't obvious looking at it. The derivation actually is relatively simple. And here it is. The expected value of x, if we go back to our definition, now I'm going to break up the integral. The integral goes from 0 to infinity since it's unilateral. And I'm going to break up the integral from going from 0 to a and then a to infinity. We can do that. We all know what we mean by that notation. So it goes from 0 to a, then a to infinity of x times the density. That's the definition of the expected value. Well, clearly, well, not clearly, we're going to throw away the x is equal to 0 to a component. Is that okay? If we do, we're throwing away something that's positive, right? In other words, I'm just going to keep this second component, x is equal to a to infinity, and I'm going to throw away this first component, 0 to a. I'm going to get a number which is less than or equal to the original part because I've thrown away with something which is non-negative, right? So therefore, I get something which is smaller than the expected value of x. Well, in this interval, this is something that's interesting. X is equal to a to infinity. So over this interval, x is always greater than a, right? So therefore, x is always going to be greater than a. So instead of x here, I put a. I'm going to get something which continues the inequality. I can factor out now my a, and what is left is the probability that x is greater than or equal to a. So this essentially proves the theorem, because the probability of x is less than a is less than or equal to the expected value of x, and then we take the a to the other side. So this is the derivation of this inequality, which is actually pretty straightforward. So that's Markov's inequality. Quadratum demonstratium. You know what that means? I looked that up using, yeah, it's Latin. I looked it up on the web. I Googled it. Thought that would impress you. I knew Latin. Okay, another tail inequality is the Chebyshev inequality. Chebyshev is a remarkable mathematician. Did a lot of great stuff in probability. And what other things does his name accompany? Chebyshev polynomials and filters based on that. And the Chebyshev inequality is also of fame for him. Nobody agrees on how to spell his name. This is the one that's used here. I've seen it spelled starting with a T, and sometimes it's CHEF, and sometimes it's T with a C, T with a S. Anyway, there's all sorts of different variations of the spelling of Chebyshev. He was a great mathematician that lived in Tsarist Russia. Tail inequalities. Chebyshev inequality says the probability, well, you can read it. The probability that this quantity is greater than a is an arbitrary number, is less than or equal to the variance of a over a squared. I don't know about you, but when I look at the definition for variance, it doesn't come out and smack me in the face that variance is a measure of dispersion. Just by looking at the definition of variance, it isn't obvious that it is a measure of dispersion. The Chebyshev inequality reveals the variance as a measure of dispersion, or how much something is spread out. If you see dispersion explicitly in a probability density function like a Gaussian, you can say, oh yeah, that's sigma squared, that tells us how much it's spread out. There it's obvious, but just by looking at the definition, many times it isn't obvious. So the probability, the Chebyshev inequality states the results here, which are graphically depicted here. We have a density function with an x bar, and the probability that x minus x bar is greater than a is the probability that these areas under the tails is less than or equal to the variance. So what happens to this bound as the variance of x gets larger and larger? It gets larger and larger too, corresponding to the interpretation that this density function gets spread out more and more. Hence, Chebyshev revealing the variance as a measure of dispersion. Here's the derivation of it. It's a little bit tricky, but let me walk you through it very quickly without spending a lot of time on the details. This is the variance of x. This is the definition of the variance of x. And we're going to divide up our interval. We divide up our interval much like what's the other inequality? Markov inequality. We're going to divide it up into here, here, and here. So we're going to divide up our integral into the variance in those three parts. Then we're going to throw away the middle, thereby saving something which is smaller than the entire three together. So that's what we do in the second step. We integrate from minus infinity to that first point, and then from the second point out to infinity. We've thrown away that middle part. And so whatever the variance is, it has to be less than that since we've thrown away stuff to get to this point. Well, this can be written as, you probably can't see it unless you've printed it out. Probably can't see it on the television screen. It's the probability that x minus x bar squared is greater than a squared. This is a summary of these two intervals. If we take these two intervals and put them together into a single inequality, we get that we're integrating over this interval. This infinity should probably not be here. It's just over this interval. And if we are indeed over this interval, you notice we're integrating over an interval. And just like the Markov inequality, over this interval, the x minus x bar, which appears here, is greater than a squared. So if we take this x minus x bar squared and we replace it by a, we get something which continues the inequality chain by putting something in there that is explicitly depicted in the integration limit. And so we're left with, it's less than or equal to, since we're integrating over this, greater than or equal to a squared. We can then factor out the a squared, and what we're left with is the probability that x minus x bar is greater than a. So therefore, this is derived in the same flavor as the Markov inequality. We, number one, throw away a part of the integration necessary for the moment, and then secondly, we recognize the interval of integration allows us to make a substitution of the integrand, which simplifies the result. In fact, in your book, this is not the proof which is given in your book. The book actually uses Markov's inequality to prove Chekhov's inequality. Very clever proofs. First time I've seen it. You might want to check that out. This is the standard textbook derivation of the Chebyshev inequality. And it's on page 137 of your text if you want to take a look at that. But it derives the two.
Does the Chebyshev also require that it be one-sided?
No, it does not. There is no requirement that it be one-sided. However, the quantity x minus x bar, if you take a magnitude, that's a random variable that is one-sided. So that's how they transform from one to the other. The x minus x bar, the magnitude, if you do a random variable transformation on that, you get a random variable who has a density function which is unilateral. Okay, Chebyshev's inequality illustrates the variance as a measure of dispersion. As the variance increases, the bound noted by the shaded areas of the tails becomes larger and larger, suggesting the distribution is spreading out more and more. So the Chebyshev inequality again reveals the variance as a measure of dispersion. Then there's the Chernoff bound. The Chernoff bound is another tail inequality. This is a tail inequality that's primarily used in the area of information theory and was first derived for application of information theory. And I'm not going to concern ourselves we're not going to concern ourselves with it here. But if you're really into tail inequalities, you might look at it. Okay, any questions on the material? Let me ask you this. Do you have any questions on the homework that you had? We have about 4 minutes left. Any questions on the homework? Okay, well, if there's no questions, then thank you very much. We'll see you on next time, Thursday.